Embarrassingly parallel problems are supposed to be easy, but there's a common pitfall that can turn idealized speedup into counterintuitive degradation. While such embarrassing problems typically share little to no state between subtasks, it's actually quite easy to inadvertently cause false sharing by accessing the same cache lines. Before we get to benchmarks that demonstrate this on real systems, we can first imagine a simplified model with 8 bytes of main memory and 2 cores with a single 4-byte cache line each. Whenever we need to load a value from memory, we don't just load that single value into the cache, but rather a contiguous and aligned block of 4 bytes. So, if CPU A wants to read the value at memory address 2, we actually populate its cache with the values from addresses 0 through 3. If CPU B then reads from address 0, it also populates its cache with the same values. At this point, there isn't a problem, as both tasks are just reading, but writing introduces a new hurdle. Let's say that CPU A does some calculation on the value it read, and wants that value to be reflected back at address 2. Just updating CPU A's cache is obviously not sufficient, as CPU B would have an outdated value. For simplicity, we can imagine CPU B's cache gets invalidated, and the updated value propagates directly to main memory. If CPU B then wants to read from memory address 1, it needs to go back to main memory even though the value it previously read into the cache was never modified. For this conversation, the exact method of enforcing coherency isn't particularly important, but there's clearly some overhead. Even when expanding the model to current 64-bit x86 platforms, with more cores, more cache, wider cache lines, and even multiple levels of cache, we can face this exact issue of cache misses caused by false sharing. As a concrete programming example, let's use a simple kinematic problem where we update a collection of points' positions based off of their velocities. The example will still end up pretty contrived, but it feels marginally better than just incrementing counters, and is still embarrassingly parallelizable. As a first baseline, we can define a point structure, its update method, and use Google Benchmark on a workload that updates a local array of these points. I've opted to keep a simple implementation to focus on the future cache interactions, but if you're interested, there's plenty of room for optimization. My favorite is perhaps reorganizing the data structure to better suit auto-vectorization, which I've covered in another video on SIMD. Back to our current example, however, we get a result just over 2 nanoseconds for a single iteration of our update loop. Before moving to a multi-threaded example, we can introduce atomics as a synchronization method. It's probably not the method most useful here, but the change is simple and is great for demonstration. All we need to do is modify the data types of position and velocity, though I'd at least opt to explicitly call fetchAdd. Doing so, instead of relying on operator overloads, indicates that there's some level of complexity that has been added with atomic variables. And technically on some platforms will perform better with an explicit relaxed memory order. But those details aren't our focus here, so we can instead just observe that with the additional overhead of atomics, we now have a baseline of around 12 nanoseconds. While not yet particularly meaningful, we can now also test multiple threads using Google Benchmark. It is important to note, though, that the results still reflect the same measurement of how long it takes a single thread to update the position of 8 points. We are not distributing the work between the threads, but rather running the same amount of workload on each to see if the performance degrades. For an embarrassingly parallel problem, we'd expect the results at 1 thread and 8 threads to remain the same, and for our example so far, that's exactly what we see. Things start to get interesting with our next example as we move away from local arrays of points to a collection at a shared scope. For convenience, we can create a class to represent this collection, but it's still fundamentally an array of points with enough capacity for all threads to have points of their own. We're still not directly sharing any points between threads, and so have to define which values each thread is responsible for. Perhaps the easiest method is to have each thread start at its index, and use a stride at least as large as the amount of threads. This creates an interleaved pattern that would also nicely handle workloads not equally divisible by the amount of threads. While the benchmark remains around 12 nanoseconds for a single thread, it also progressively gets worse as we add threads, with 8 resulting in roughly 100x performance decrease. It's not just that the problem doesn't scale well with more threads, but that the supposedly independent workloads are somehow impacting one another. We can highlight this issue further with the analysis tool perf. Focusing on the data cache closest to the CPU, we see that we had around a 20% miss rate. Granted, a larger stride is fundamentally less cache-friendly, but the single-threaded results don't show the same impact. Clearly there's something to dig into. Perf C2C allows us to do just that, and look into the cache line contentions. There's a lot of information here, but at a high level all we'll be focusing on is that there are hit-M events. These indicate that there would have been a cache hit, but another core owns a modified copy of the cache line. We're seeing a few cache lines that have these events and can drill into one of them. Again, there's a lot of information, but for simplicity, all we really need to note for now is the symbol column, which is confirming all of this is related to our update method. We could further tie these cache lines and offsets to our point structure and how we're iterating over it, but this feels like enough evidence at the moment that we are seeing false sharing. Even though no two threads are accessing the same memory addresses, they are accessing the same cache lines, and many of the updates are causing caches to get invalidated, resulting in more memory reads and thus longer execution times. With that being the case, what happens if we change up our access method? Our interleave pattern is surely increasing the chances of hitting the same cache lines between threads. So what else can we do? How about we assign contiguous chunks to each thread instead? Again, the results start around the expected 12 nanoseconds, and while it's not as bad, we're still seeing significant degradation with more threads. With 8, we're now seeing a roughly 10x difference, which is at least better than 100. Following a similar pattern, perf does show that we're still seeing plenty of cache misses, but not as much as before. While this is still showing the very real effects of false sharing, it's also probably highlighting an unrealistic example by using such small workloads. Logically, all of the contention is now isolated to the start and end of each chunk being processed, but with such small chunks, that's practically everything. Just increasing the workload per thread can show a very different story, so it's rather important to understand what you're testing and why. It's easy to introduce biases that may not reflect the same situation that you intend to use the results in. Now, to be honest, this might actually be good enough for many real-world applications. But let's go back to our smaller example and focus again on why there's still any contention to begin with. To do so, we need to touch on the topic of alignment, which dictates where in memory data can be placed. Floats, for example, have a natural alignment equal to their size, so are on a 4-byte boundary on x86 systems. Our data is effectively an array of floats, and so is only guaranteed to start on a 4-byte boundary. With a 64-byte cache line on x86, there are plenty of arrangements that lead to our chunk sharing cache lines. We can, however, enforce a stricter alignment on our array, and force it to start on a cache line boundary. Here, we explicitly use 64, but the constant stood hardware destructive interference size and constructive interference size exist for portability, though are quite a bit more verbose. This doesn't help our larger stride access method, but we do see chunking finally avoid any performance penalty. As expected, this also means that our cache miss rate is nearly 0%. We do again need to be careful though, as these examples conveniently use the chunk size that is equal to the cache line size. Each thread is responsible for 8 points, which in turn are made up of 2 floats that take 4 bytes each, totaling 64 bytes, the same as our cache line. If we were to even change this to 7 points, we'd be back to problematic performance caused by cache misses. Going a bit overboard, at least for this example, we could instead change the alignment of each individual point so they'd be on separate cache lines. For such a small example, this works alright, as we avoid any cache line contention, but we also waste a bunch of memory and avoid many benefits of having contiguous data. If we want to keep some of these benefits, we could instead use a thread local data structure that ensures each thread has its own array of points. This does make it less obvious how we expect these points to be later shared, but unlike the local arrays we started with, this does still have a broader lifetime and can be passed around via pointers and such. Perhaps not a great use for this example, though it does demonstrate the performance is as expected without any false sharing. Along the same lines, but with a bit less convenience, we can manage the same idea ourselves with another level of indirection. We can create our own separation of arrays for each thread and reference into it using an index, much like we did with earlier examples. Borrowing another concept, we can align each of these subarrays, which now has the effect of preventing false sharing, even regardless of how many points each thread is responsible for. And with that, I'd say we covered quite a bit on how data layout can impact performance due to false sharing. Granted, many of these examples were specifically crafted to demonstrate certain points, but the concepts are the same nonetheless. The biggest takeaways may not be the individual patterns presented, but that there's yet another reason to be mindful of your data. If these types of topics interest you, perhaps you'd like to check out this video that dives into vectorization, or this other video that YouTube recommends. And if you want to help keep me motivated in making more hobby videos like this, feel free to subscribe and/or comment down below. Until next time, take care.